show of hands, who has a laptop here? I'm like 3 people. Okay, so if you want to play along.
Hold on, Hein. I need to
What?
introduce you, goddammit.
Okay, but I have to set up. So before you introduce me, play.golang.org, like that URL over yonder. Okay, Jade, go.
Cool. So, thank you everyone for coming. This is the 4th Rabbiteer session of the year, and as a company, we really like languages. We really like new ones. We really like how they change and how they've grown. We like updating them. Hein is our Go expert. When he got here, I think he convinced one of our clients that we really needed to move to Go, and now we're currently migrating the entire server to Go. And that's because it's a really cool language. So yeah, so hopefully if you've got laptops, follow along. You'll be able to play around. It's a really cool thing to learn. And yeah, take it away, Hein.
Cool. Thanks. Okay, you can also do this on a phone, although exactly coding on a phone isn't that much fun. So play.golang.org is sort of a sandbox environment where you can just execute code and run it, and it gets compiled and the result sent back to you. So that's just a simple result. But yeah, anything you see me demo today, you can probably run in there and play around with it. Okay, so on to my slides. Go, the language you never knew you loved. Probably because you've never heard of it. The universities aren't that up to date with languages and frameworks and tools and whatever. So generally what they try to teach you. So yeah, this language is not that old when you compare it to something like C++, but I think the first line of Go was written like 2003 already. So in some senses it's old, in some senses it's relatively new. Yeah, so I'm going to run through some code to give you an idea of syntax and what you can do in it. So I'm going to try and explain an entire language to you in a relatively short amount of time. Then give you some links to follow if you actually want to learn to use it, because this is going to be too fast for you to entirely understand language. And then I'm going to do some tooling around the language, because a lot of the things I enjoy about Go is not just the language, but the things around it, things that actually make it fun to use it. Reasons I don't like some other languages are mostly the environment you work in. It's not the actual syntax. So, okay, this is a simple hello world example. Let's see if I can zoom. Yeah. Nice thing about these slides is you should see I can run code inside them. So, package main, everything comes in a package. If you're familiar with Java, this should feel roughly familiar. You have import statements to import libraries, similar to other language. Func main is always your entry point, and simple format of print line hello world. So I'm assuming there's no questions surrounding that. So type declarations gets kind of interesting. You start at the top, var, variable type, variable name, and then type. So you could say var j int and then assign it. You can also do this in one line, which might be easier. Since we actually know what the type is of the right-hand side of the assignment, we can infer that type. So that's a very handy thing, which allows us to just not say the type. So we can just say we have a variable called L, and it's the same type as whatever we're assigning it to. Or we can do it even shorter and just colon equals. So that's declaring a new variable of the type of whatever is on the right-hand side and assigning it all in one line. This is a printf, if you're familiar with C, very similar in syntax. Capital T gives us the type of that variable. So running this will just give us int, 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 because all those variables were declared as ints, including m, for example, that we didn't specify type. So it did have a compile time type, but it was all inferred from the code itself. Any questions surrounding this? Okay, there's one more thing you can do. I didn't make this code editable, but you can do multiple variable declarations on one line. So you can say k, l, colon equals 1, 2, and that would then assign. And this is useful in some other cases, which we'll get to later. Looping is similar to some of the language you've seen, although while loops, they do entirely different. We'll work from the inside out. So for loops, simple assignment, conditional, and increments. With a simple print line, just for example. While loops, however, are a slightly strange syntax because they just say for and then whatever Boolean value, so for true. And because indefinite loops are sometimes handy, you can also just say for. So this just loops infinitely. You can run this and it will output 0 to 9. Any questions around looping? Cool. I didn't expect any. Okay, so functions. You can declare standalone functions similar to some imperative languages. Func keyword says it's a function, says the name of the function. Parameters, and similar to most other types, are the other way around from C++. You have variable name type name, and yeah, that might be something to get used to once you start actually coding it. And yeah, simple function call similar to what you'd expect in other languages. I'm going to jump over the slide. I forgot to reorder them. Functions, however, can have more than one return type. There are a few other languages out there, but they sort of hack this. This is actually part of the language and not tuples like you get in most other languages. So most other languages where you can return multiple types, what they do is they just take the two types, put them in a tuple, and essentially return one value, but it's a tuple. Where here you're actually returning two values. So you have a function. Forget this part for now. When I wrote this, I was a little bit in a hurry. My apologies. So you have a function returning two types, a string and an error. And this is very useful, and I'll get to why a little later. I just want to introduce the multiple value returns from a function, because in this, like this example, you have the actual value you're interested, which is some string getting the name from a client or something like that, and something might go wrong. And returning that as an error rather than throwing an exception is a really interesting concept, because you can then treat that error as a value. So you can say, was this error, like if error not equal null, what do I want to do?
So
do I want to retry?
How does that differ from just having an abstract class in Java and then overriding it?
Write that code is a lot more logical than really throwing exceptions. I'll maybe show an example later. So you also get type aliases. Although they introduced a new type of type alias in later goes, but I'm just going to cover this one. So we declare a new type called in, and it's a function that returns a string. We return a new, or we declare a new type that is a function that takes a string and returns a string. Okay, everybody still following that? Okay, cool. So we can define a function that takes as input another function and outputs a function. So functions are first-class citizens in Go, and you can assign them to variables, you can store them, yeah, and work with them as if they were an integer. For some people, this might be a relatively new concept. Unfortunately, I don't really know how to explain it. It's something you really have to work with to get used to, and once you're used to it, it's relatively powerful. So we write a decorator that returns a function that will take the output of the function passed in and append it to both sides. So if you have a function like we do here in the main that returns just a pipe, it will take the pipe, put it on the left-hand side of the right-hand side of whatever the function it returns is given. Think about that for a while. Cool. Okay, so here's the function that will get returned. It takes some sort of string and returns a string. And what it returns is the result of the function call that was passed to this function, plus the string that this function was passed, plus the result of this function. Okay, so then we can use it like this. We create a decorator, and we want to decorate using pipes, and this gives us a function. So what is assigned to this variable is a function we can call like this. So passing it a value. So if you run this, pipes are appended to either side of the string. Any questions surrounding this? I expect some. Yay, nay. Cool, cool. Okay. Yeah, multiple return types. Okay, so unlike a lot of languages you do know, object orientation isn't really something Go does. So typically in C++, Java, and a lot of others, you have inheritance, and you have sort of, I can assign a sub type to a parent type, and then still call this functions. And there's some of what is useful to that in Go. So what we like about this object orientation is that if there's something in some parent class, we can just inherit from it, change the functionality a little, and just continue with our lives and reuse essentially that functionality. Also, if we write a function, we can take in a type that is of this parent class. But if anybody inherits from it and passes that as a parameter, we'll just happily call those functions. So two of the features in the sense that object orientation gives us is code reusability, so reusing code in this parent class, and dynamic dispatch, so at runtime deciding what is going to be called. So we don't at compile time know which function we need to call. We can decide that at runtime. And runtime, if you're writing a library, might be 2 weeks from now or a month from now. It might be someone else's code, most probably someone else's code if you're writing a library. So those are useful things to have. So how do you do it if you don't do strict inheritance like one normally would? So let's go to what is the closest thing to classes. We have this thing called structs. Now, if you know C, C also has structs, and this is essentially just a container with a list of values in them. So you can have variable name, int, you can declare it like this, yeah, and it prints out 0, 1, similar to what you expect. So this is initializing a struct with values corresponding to that. Let's see if I really want to edit this. Yeah, okay, you can also access member variables, similar like you would expect in other languages. Yeah. Yeah, like that. Yeah, so pretty much structs, pretty much similar behavior to object orientation, so nothing strange there. We can define functions on these structs. So this is what they call the receiver, so the type that the function is going to be called on. And you can define a function very similar to the way we defined functions earlier, a name with some return type. And we can then access the receiver, variables from the receiver, and do some operations with it. Yeah, so we declare it with 2 and 3, and call the function twice as nice, which just multiplies 2 by 2 and gives us the output. So relatively simple. Any questions? Yeah. So it is relatively similar in some senses what you achieve at the end. But when you declare an abstract class and you have a subclass that then overrides, at runtime, you have to do a type lookup on that variable to see what is the actual type, because it's not the abstract class, it's some other implementation, and then only can you do the function call. So there is that additional lookup, which does give you some performance penalties. No, but even if you don't do even if you don't do casting, so if you have a subtype B of type A, you have a variable of type A, and you can say a dot, or you call a function on A, it still has to look up the concrete type of that variable, because it's not known at compile time, so it has to happen runtime. So that is one downside. Go has a similar thing that does happen, because you do need sometimes that ability to do a runtime lookup of what do I need to execute now, because not everything is known compile time, obviously. But if you can exclude that a lot of the times, it really helps. There is a point that I'll get to about abstract classes and the way that differs in what Go treats as an abstract class, because it has a similar need for that, but it does it in a slightly different way that is actually really powerful. Okay, so about reusability, if you have some struct you would like to add to it, you can take the struct that we've declared and just embed it in a different struct. So that will have all of the same values as the original struct in the new struct, but also allow you to do things like this, functions that weren't defined on this type being called on it. And this is not a lookup on my struct type, it's essentially defined on even better. Yeah, the type we defined here. So this allows you some reuse of other types, which is pretty useful. So here we get to that abstract class. How would you do this inheritance where you generally have this function taking type A, and we want to inherit from type A to extend that functionality or change it completely. So how do you do abstract classes or interfaces, as they're called in Java? So if you know Java well, okay, how many people here have done Java? Okay, so I assume most of you have encountered the interface keyword in Java. So interfaces in Go is not at all like interfaces in Java. They share the same name, but that's roughly where it ends. We here have encountered traits from functional languages. Okay, like one person, 2 people, cool. Okay, so interfaces are closer to traits than really to interfaces in the Java context. So we can define an interface, and in it we give a list of functions that we want. Their names, the type of the parameters they need to take, and the type of parameters they need to return. And this is all that an interface is. It just says whatever is given here, the value that's given here has to have this function defined on it. And that essentially is a list of requirements that you have of this type that's being passed through. So we can define a function that says we want some variable, and it must be of this interface type. The only thing we know about the type being passed through is that it will have this function defined on it as given by the interface. So similar to abstract classes, this would be some abstract class. The interesting part about this, however, is that both these two types implement that interface, even though nowhere we have explicitly defined that they do. So they, by their very nature, by having a function defined on them called twice as nice, taking an int and returning an int, it already implements this interface. And the reason this is a very powerful concept is normally if I have a library A, and it gives me some very useful function, it will take an abstract class in Java terms. And I will have another library that gives me some useful object. But because this library doesn't inherit from this type in Java, I can't just feed this object to this type. I'm going to have to define wrappers around it or do some inheritance or like really do some work to get this type to match the type that this library is expecting. Even though it has all the right functions and all the right functionality on it, these two aren't entirely incompatible, even though they really should be. Using this way in Go of defining interfaces, this library just says, I need some type, don't know what type, just some type with this function on. A different library can then define that type and the function on it, and then allow you to use these two libraries together, even though they've never heard of each other or been developed to use together, and they'll just run together. So that's the idea of using interfaces. That's the reason, really, the power behind interfaces and why it's different from an abstract class. So instead of having this library needing to explicitly say that it implements this interface, it just does so implicitly by defining the right functions. Yeah, so an example of running that, we can define the two types, pass it to the same function, and okay, you probably didn't look. So multiply or mul2 actually multiplies the number given to it by 2. Liar actually multiplies it by 3, not 2. So we can define these two types, instances of those two types, and pass it to the function. So both are supposed to output 4, right, not right, which is the liar does not, and right, which is mul2 does. So, yeah. Any questions surrounding that? Okay. So in the slides, I only show some snippets of the code because it doesn't fit on one slide. So all in all, that would be the code. Let's see if I can. Yeah, no, it doesn't fit on the projector either. But yeah, so you still have the package main importing and then just defining the types and the function. Just in case you got lost by the way the slides are looking. Yeah, the code is still similarly structured. They're just split up into blocks so they nicely fit on the slide. Okay, so concurrency. One of the nice features of Go is how easy it makes concurrency in general, how easy it makes to run things concurrently. So if you've ever done C or C++, starting up a thread is painful. And it is not very flexible and takes time. I see two people that have done that before. Like, that smile is one of pure pain. So it is not fun. It is better in Java. I must say I've been impressed by Java's atomic library. But yeah, so threads are generally not easy to start up. Also, threads are quite heavyweight. So back in the day, before event-driven programming, sort of the limit of the number of concurrent connections you could do to one web server was 10,000 connections. That was sort of when you hit the limit, because that's how many threads you could spawn. If you spawn like 10,000 threads, your server is pretty much on the limit, and that doesn't matter what hardware you had at the time. Like, that was the limit, and if you could code 10,000 connections on a server, you were godlike. Like, it was the limit. Because threads are like, the limit of threads are roughly 10,000. So you have to really think about when you're using a thread, like, can I start up a thread? How many have I started up? How can I reuse this? Because starting it up is expensive. Shutting it down is expensive. Having just too many of them, even if they're not doing anything, is expensive. So we don't really like threads. We do all sorts of very smart things to stay away from threads. If you're interested, that's why Node.js is at all useful, because it's actually single-threaded for the most part, and you just have this event-driven programming where everything's just happening on this one thread, and you're just constantly switching between serving different clients. And I think they've gone up to like 1 million WebSockets on like one node server, which is, you know, relatively impressive. But it's mostly because of the event-drivenness of it all. So we like this idea of staying away from threads because we know that their limit is like 10,000, and we really like to do 1 million or up. So Go introduces the idea of a Go routine. So if you've ever heard of the word coroutine, that's an idea from functional programming languages, generators as such. It's very similar to that. So yeah, clarification for those that haven't heard of that. For those who have not, a Go routine is essentially an application level thread. So it's a lot lighter than a standard system level thread, and it allows some really interesting semantics. So starting up a thread, or Go routine, let's be accurate, Go routine. So we can define a function just for interest's sake. We say time.sleep, we just wait a second and we say hello. Relatively simple. So we can time it, we can say let's start, and you just say go. Go and function, and it is that simple. Right? Yeah. So starting up a Go routine is relatively painless. It's like 2 letters, and that's all. So some downside to this is that's all the control you have. Where on system level threads you can set priorities, you can set affinity, you can do all sorts of really complicated stuff. But that's why it's heavy. That's why it is expensive, because there's an entire scheduler and a huge system based on that. So it takes you 200 milliseconds to start up a thread because it has to do all of that work to get things right. This, I'm not even sure how little time it takes. I think it's 1/10 of a millisecond. You can start up a Go routine. It's fast. Okay, so we can run this same function twice, and we can time it using the time library. The very nice function is time since, and you give it a time, and it'll tell you how long. Okay, I have things to throw. Keychain. Keychain or pin? Vote real quick. Keychain, pin. Keychain. Okay, cool. How long do you think this will take to run? And what? Not that fast. Yeah, but 1 second? Okay. Any other votes?
I say less than a second.
Okay, so that function is waiting for 1 second, right? Yeah, I'll give. See, it doesn't like. Yeah, there, okay. Okay, I heard a 2-second vote. 2 seconds. Oh, 0009. Wait. 099999?
0.0009.
Okay. Yeah? Okay, so roughly 1. Okay, you're saying roughly 0. Okay, what do you think the output will be for Mr. 0 and Mr. 1?
Is it waiting for the threads?
Shh, Jade, you know too much. Go.
I don't. I haven't learned it yet.
Okay. Mr. 0 wins. Oh, shit. I can throw, so sorry. If you died today, it wasn't me. So, Jade had a good, correct guess. When the main function ends, your application ends. So when these two say, they get kicked off, and the main function just exits, and nothing happens. So that was a trick question. That is why the question was there, so I don't forget and embarrass myself. So here, same function. A little messier, I must admit. I'm not entirely happy with the way I fixed or put this together, but this is typically how you would send two things that you don't actually, you're not waiting for a result from this function. So this is typically how you would do it. Yeah, they have this nice package called sync for all your synchronization needs, and you just tell it you're going to wait for two things, you kick them off, you pass that through, tell them to tell you when they're done, and you wait for them. So this actually takes 1 second, 0.0002, whatever, 2 high there's. So there is still some work, still something you have to do about getting the Go routines that you're kicking off, getting what they're doing back to you, and yeah, doing synchronization work. So it's not an entirely thoughtless process. It's very easy to write code like this and going, but nothing's happening. I'm pretty sure I'm calling the functions, why isn't it happening? Okay, so in this example, we didn't actually need anything from say hello, we just wanted to wait for it to be done. So there are different tools that are given to us by Go if you actually want to wait for something, or if you need to pass information from one Go routine to another. So Go has this idiom, if you want to call it, saying don't communicate by sharing, share by communicating, which makes sense if you know what they're saying, I guess. So the tool that they give us is this type called chan. I assume you all know what a queue is, like a FIFO queue. You put something in, you get something out. It is pretty much the same as that, except it's thread safe. So you can have multiple writers try to put things in this queue. You can have multiple readers try to read out of this queue. But it's built into the language, and it's a very handy tool. So what we like to do is we declare two variables, the things to say, and output, the things we're done saying. That's going on to somewhere that is not us. And that's, I feel, a large part of what makes Go nice is that you only really need to look at this function to care what it's going to do. It is going to close the messages that are going out. It's going to say it's done. Oh, I have to introduce the defer keyword. I'll do that in a second. One can also range over a channel. We can range over maps, arrays, and channels. So this is similar to your for each loop in most other languages. So for each element in this queue, note that this queue can still have elements added to it, and we will essentially wait for this element to be added. So if this thing is empty, this for loop will wait for some element to appear in this queue from the outside. And we will simply print whatever was in the queue and output that same thing on to the next part. We can also define a function that just outputs a lot of strings. So we just keep adding things in this queue. So you will know, okay, go back to the defer keyword. In C++, you have objects being deallocated when it goes out of scope. This is generally used when you want to free resources when there's an exception thrown. That's typically where you'd use it. So if an exception is thrown, everything that gets popped off the stack gets deallocated, and they're destructor called. We don't really have destructors in Go. Go is entirely garbage collected. I forgot to mention that key point. And that's another thing that's very handy in a language is not having to worry about when to deallocate a pointer. It becomes even harder to know that when you're working in a concurrent world, because two things can access it at the same time, so you don't know when they're done. So having a garbage collector sort that out for you is really handy. But we still need to have things be done when we go out of scope. So we have this defer keyword that says, when this function ends, run this other function. So this says run close of that channel once this function exits. So once we're done saying all the things we want to say, just close the outgoing thing. Similar to this, once we've loaded all the words, say that we're done. It's a way to signify that we're done sending messages on this channel. Yeah. So this allows us to write very simple things like this, making a word list and a done list, getting words in this word list and saying them and telling that we're done. So simple output. Are you having fun yet? So this might not seem like a very interesting application, but imagine getWords was loading these words from disk or a database sitting in the cloud. That could take time. So if we waited, if, for example, getWords returned an array, we would only be able to access these words and start processing them once all of the words were retrieved from the cloud, or all of the words were loaded from file, or all of the words were in memory. Now we can load a terabyte file, one word at a time or one line at a time. And we only need to output this one line at a time. So we can process this terabyte file without using more than a kilobyte of memory, because we're only processing one line at a time. So that's the one advantage, is we can process huge files and a lot of work without really keeping all of it in memory like you do in an array. The other advantage is that you can start sooner. Let's suppose after reading the first two words, the disk takes a long time, or you have to do an entire rotation and it takes a large amount of time to do. Then if you're loading that into an array, you'd have to wait for all of that, where you could start processing the first word, in this case displaying it, which doesn't really take time, but let's say you were doing something really complex with it. You could start doing that with the first word before you loaded the second word. You don't have to wait. Question?
For any one of those, because I'm struggling to make out what's what.
Yeah. Okay, sure. So func declaring function. Say is the function name, so that's how we'd call it. For example, there is the function name that we're declaring. These two are variable names. So this one, you don't have to define the type if it's the same type as the next one. Sorry, that might not have been very clear for an explanatory slide. So there are two variables, one called toSay and one called out, and they're both of this type. So that's actually one type. It's channel that contains strings. Okay, and it returns nothing. So after the parameter list, there is nothing. So it doesn't return any values. Okay, is that clear? Cool. Would you like me to explain getWords, or are you?
No, I get it.
Cool. Okay. Thank you for the question. So similarly here, say outputs a list of the things that it has done, so that we can just go over all of them. And this is essentially waiting, counting how many words we have done, so that the main function doesn't exit. This needn't be the case. One could theoretically, instead of kicking off say in a go routine, one could have it just take a word list in, words to say, output nothing to no queue, and just block until it's done saying, until it has gotten all the words. Yeah.
Sorry, so it's passed by reference.
What is passed by reference?
So it's word list and done.
So channel is a...
Too late. Guys, if you want to ask a question, if you put your hand up, I will bring you the mic. I promise.
Cool. Okay, so the question is the channels passed by reference? In some ways they are. Underlying to that channel is a pointer, if I'm not mistaken. So you're essentially passing a copy of that pointer along. So it's not actually reference in that sense. I don't think anything is passed by reference ever in Go. It's always by value. So if you have a pointer to something, you'll make a copy of the pointer, but obviously not the value. So and that is an entirely different and very interesting discussion that I'm resisting having, because I think most people won't necessarily find that interesting. Screw it, why not? So if you have a function, and you have t, which is a pointer to an int, declared something like that. Is this declared on the heap or on the stack? Who would like to guess? No, it's declared on the stack. One would assume that everything that's a pointer, similarly to C++, similarly to anything allocated with the keyword new, would immediately go on the heap, because this is what we needed to do in C++. C++ doesn't have that intelligence to know when something has to go on the stack or once it has to go on the heap. It doesn't know the end of lifetimes of things, because we have to delete it, all of these kinds of things. Because of this, because this is garbage collected, they built some intelligence into the compiler. So it knows that this variable doesn't live longer than the function. So if it is declared on the stack, it will die with this function. So it is not. So even though it's a pointer, it is not actually leaving the function. So it's a lot faster than trying to declare something on the heap. This actually doesn't do any garbage collection related work, because it just lives and dies with this stack. It gets allocated with the stack and dies with the stack. So it's a lot faster. And obviously, because if you declare a lot of things on the stack, it'll all go into cache lines. Now I've lost most people. Cool. Yeah. Okay. So. Oh, yeah. Question. Sorry.
Hi. Do you have to deallocate all the memory that you allocate? Is it like dynamic or?
So no, you don't have to explicitly ever deallocate any memory, which is part of the niceties of Go. So there is a garbage collector that it is a scan and sweep garbage collector. For those of you interested in garbage collectors, it's a 3-phase or 3-color garbage collector. I forget the right terminology. So essentially what it does on a semi-regular interval, concurrently to your application running, is look through all the memory that you've allocated and look for any pointers that or any pieces of memory that you're no longer using, and then it deallocates that. There are some pros and cons to that. Yes, continue your question.
Does it do that after the function dies or after the program is done?
No, while the program is running, even while the function is running. So if I were to allocate memory, it would depend on where it's allocated. So if it's allocated on the heap, it will be deallocated while the function is running if we're no longer using it. If it's allocated on the stack, it will die when the function exits. So specifically surrounding stack things is that it lives as long as the function lives, where heap things will get cleared as the program runs. Yeah, so there are a few other languages that do garbage collection, actually quite a few. A lot of them do reference counting. So that is where every time you assign a pointer, you increment a count. Every time a pointer goes out of scope or gets reassigned, the old value gets decremented. If it reaches 0, we know nothing is pointed to that memory, and we can just free it. It's a very nice way of doing things. That's also where you get all these things like weak references, where you do get a reference to something, but it doesn't increment the counter, and all sorts of very strange things happen. And it's a lot of programmer work to keep track of that. Also, every time you do anything with a pointer, essentially, there is a value being incremented and decremented, which can be expensive if you do a lot of pointer assignments or accesses and a lot of that in like loops and things. So in this way, you don't have that, which is a pro. The con is that you do have this garbage collector taking up some CPU time. Thank you, Jade. Okay, I have to rush since there's only 23 minutes left. Okay, so suppose you have a generator of information. So this could be something like metrics from an application, something streaming in over time. So in this function, I'm just every 100 milliseconds outputting a random integer. So we want to be able to batch process this. The code is might take a little while to understand. If you're just looking at it, we'll go through it line by line. The purpose of this is a lot of time inserting, say, into a database is a lot easier if you do it in a batch. Instead of writing something every 100 milliseconds or every millisecond, you want to do this every 50 milliseconds. You want to just take a bunch, get one write lock on the DB, just put all of those in one transaction, and then continue. This can be a lot faster and save you a lot of time. So if you were to do that on some other language, you'd have some endpoint data streaming in, and then after the 100th one that comes in, you do this transaction. So every 100 requests would have this spike where it's actually inserting into the DB, and all the other ones would take time to, or will take almost no time because it's just adding it to an array for once it will actually do something with it. And then one shot, there's this one request that's just going to take a lot of time. So if you have some other part of your application, or even a third-party application, something outside, waiting for this request to finish, and it does take 200 milliseconds, that could be relatively negative to your performance. It might be noticeable, say, an app pauses for 200 milliseconds to upload data because it happens to be the one that was unlucky and had to do the request, for example. Anyway, so we want to batch things. So we can define a ticker. This gives us back a struct with a channel in it, and every 500 milliseconds in this case, the current time will be output on that channel. So this is a way for us to get periodic things on a channel. We want to have this array where we're going to batch things up with. So our numbers are coming in through this channel. Quickly, the function interface called batch takes a channel of integers called numbers, and it outputs batches. So all this thing does is it takes in integers and sends out batches at the other end. So we get in numbers, and the simple thing is when we get in a number, we just append it to the batch. So very quick operation. It doesn't block this channel, it doesn't block this generator, all of it just continues. Then when the timeout, the channel that we get the time of every 500 milliseconds, gets the current time. We don't actually do anything with it. We just want to know that it is now time. We take the batch that we've been building up and we send it on. So we've been building up this batch over 500 milliseconds and we say, okay, this is the current batch. Do this batch. Whatever is done with it, we don't care. That is someone else's problem. So once again, it's relatively quick for us. Someone else will do the work. Then we just start a new batch and we start a new timeout. So we reset the timer, essentially. I think there is a better call. I wrote this without internet because, long story. So I think there is a timeout.reset that you can call that will reset the timer, or you can just allocate a new one. Okay, so this is roughly how you use it. You'd make a channel of numbers that you would then generate. You'll make a channel of batches. You'll batch them, and we'll print them. So then here we should get every 500 milliseconds a batch with roughly 4 to 5 things in them. So yeah. The advantage of these channels and building up this pipeline, because we're doing 3 different steps in this case. We're generating numbers, we're batching them, and we're displaying them. So none of these in this particular example is really time consuming. Generating the numbers are CPU inexpensive. Generating the batches are relatively cheap and displaying them are cheap. But if they were not, suppose that generating them was expensive, we didn't want to hold that up by the second part in the pipeline. And all of this can happen concurrently on different values. So we generate the first array, or the first integer, and pass that along. And that is already essentially being batched. Even though we haven't even generated the second number, the batching process is already happening. And I know appending to an array is a relatively simple operation, but it needn't have been. And similarly to processing a batch, if that took 400 milliseconds for us to display a thing, we would have still been generating numbers. We would still have been batching them, and then passing them to a function that takes 400 milliseconds to display them. And all of this would have happened concurrently. So it's essentially a free concurrency that we get. We don't have to really think about how generate numbers are going to impact batching, or batching is going to impact displaying them. And that's a lot of times the difficult part in writing concurrent programs is that one part is going to influence another. You can't just call a function and change a thing because the other person might not be ready for it, and you have to think about all these things. Where now we can write these functions saying, I'm just doing my thing and passing it along, and I don't have to really care where it's going. And that is really useful when you're writing concurrent applications. So if you are interested in Go, I'm not done with my talk. Far from it. I'm really rushing. This is where to start, though. So I've covered pretty much the language syntax, which is, in my opinion, the most boring part of a language, although Go is pretty interesting. If you're interested in actually looking at Go, there is this page called Tour of Go that, similarly to what I've just done, gives you a playground to run things in. It gives you examples, asks you language, and then gives you things, explains all of what I've just covered, just in way more depth than we really have time for in an hour. Yeah, and there is quite a bit of this. So I would really suggest go through this. Once you've gone through this, you'd be relatively comfortable writing pretty much any application in Go. You might forget some parts of it and you quickly want to reference back to it. Effective Go has a nice index page listing all the things you might need and some examples and things you might have to think of. I've referenced this probably for the first 2 years in coding Go, like once every month I would forget how something looks or how something works. I know most of it, but there's this one thing I really want to know. This page is pretty handy. The documentation for Go is pretty simple because of their environment. Sorry, packages. So a lot of what makes a language fun or not fun for me personally is the environment you work in. So the reason I don't like C# is not because of the syntax, it's because the IDE is terribly slow. The compiler is terribly slow, and a lot of things will just break on you. There's incompatibilities between this and that. It doesn't have this thing, etc. So it's not really the syntax of the language. C# as a language is fine, but the environment is really what gets me. So one of the things that Go has is generating documentation. This comes with the compiler. So this style of documentation that you'd see here, these are all packages, part of the standard library. Buff.io, why not? So it will have a list of functions and description of the functions and their definitions, and you can click on types and navigate to that, etc. So this, because it's a tool that is part of the standard library, is something everyone uses. So it doesn't matter what package you're trying to look at, everyone's documentation will have this format. And that is pretty useful, so you don't feel strange looking at someone else's packaging, like, where do I find this thing I'm looking for? Yeah, and it also allows you to run code inside of the documentation. So there's actual like code examples built into the documentation. And yeah, I feel that that environment that Go generates or created encourage people to do this. So you typically find very nice documentation in this format with examples running, etc. That is pretty great to have. Another thing I would like to show. So here we have an example called, it's a file called struct4. Sorry, it's really blurry. But we can mock up the formatting. I don't actually know how much I can break this. Yeah. So we save this. In command line, we can go, kick the table. Go fmt for the Go formatter. And it will format all of the code in this particular folder, which is all of that, and tell you all the files that it has changed. So it has changed 4 files, code that I've written that wasn't according to spacing, etc. So all that spacing, things that we broke, it fixed for us. So a lot of IDEs, I'm here using Notepad here. There are plugins for Visual Studio Code, for example, etc. Every time you save, they'd run this formatter. So everyone's code, whether you're writing it or someone else is writing it, has this structure that is right. There's this saying, Go's format is no one's favorite, but it's everyone's favorite. Because everyone has to pretty much uses it. They don't have to. It will compile even if it's not rightly indented, unlike Python. The compiler, in my opinion, shouldn't break if your white space is incorrect. But it does give you this nice tool to do formatting right. And I am really bad at formatting. So having a tool that defines that for you is really handy. So it's nice to be able to just write code. And I'm writing about what I want done, not how my coworker wants to look at it, because that is what happens in a lot of other places or languages. Okay, so hopefully that gives you enough kickoff ground for the language. Now, tooling around the language. So threading is very hard. You get problems called race conditions. So two threads are trying to access the same variable at the same time. Both are trying to increment it. They look at the value, they say it's 0. Both say, okay, the new value should be 1. And they both set it to 1. Really, the value you wanted was 2, because there's 2 threads. So in this example, I have a function that waits a millisecond and adds 1, and a function that waits a millisecond and subtracts 1. And we're running both at the same time, and every second we're outputting that value. Now, demonstrating race conditions are, it's actually breaking. Cool. So you'd expect it to consistently give you 0, because we have 2 things every millisecond, adding 1, subtracting 1, right? So we should stay at 0 all the time. As you can see, we are clearly not staying at 0, and we're actually going all over the show. These kinds of problems are really hard to find if you don't have any tooling helping and if your application is huge. So here I'm doing a very terrible thing of accessing a global variable called count and just incrementing that. But if you have that, that means anything in your package can change this variable. So how do you know where this is even coming from? If you have 40,000 lines of code, literally anything could be changing it, and you don't even know where to start. There's 40,000 lines, and you're going Control F, count, next, 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 and hoping you see something. Not the best way to do things. Okay, so Go, however, has this tool called race, which is a race detector. And it gives you output like this for that application, telling you that a write happened by a Go routine on that line. So that line was trying to write to it while this line was trying to write to it. Unfortunately, the slides do not have line numbers, but we can find the function. So it said line 21 and 12, and hopefully I haven't changed this. Yes, I did. Okay, so we can go run -race with race.go. What's the file name? So this is outputting that. Let's see if I can. Okay, so once again, it said line 20 was trying to read while line 13 was trying to write. So if we go here, line 13 and 20. So line 20 was trying to read while line 13 was trying to write. So you actually have like line number where things are going wrong. And literally the only thing I did was say -race. So instead of spending like hours banging your head about why this thing isn't going the way you think it's going, just one line in the compiler and it just gives you the answer. So that is pretty nice. Things to note about the race detector if you're ever trying to use this: don't do it in production. It uses 8 times more memory than you'd normally use, and I think it's 4 times slower in memory accesses. So it's not great for performance, but it does allow you to find problems that is impossible to find a lot of times. There's actual challenges where people write code and be like, where is it breaking, without using the race detector, like without cheating. And like people just go like, no idea. Like you can look at the code for like hours and hours and not find where it's actually going wrong. Yeah, so having a tool that does that is amazing and is part of the really good parts of Go. Okay, web server, 2 lines of code. That's a web server. So I have to allow access. I'm listening on port 8080. Wait, that was the web browser. Localhost 8080. Serving files in 2 lines of code. Yeah. So telling it everything that hits the root, I want to have a file server on. You can actually do that in 1 line of code, like merging these 2 lines by placing that bit in there. But since that's not typically what you do in production, I figured 2 lines is more fair. So you have this application running in the wild. Clients are hitting it and they're complaining. It's a little slow. How do you know why? You don't really. You can guess, but you don't know what part of your application is really making things slow, what is taking time. Or you see your CPU is spiking to 100% when doing a request, even though you really think it shouldn't. Or it's spiking to 100% for like 4 seconds instead of a millisecond that you expect. And trying to figure out why by looking at code is sometimes really difficult. So we get profiling tools. For a lot of languages, that is a third-party library that you have to get working with your code, doing all sorts of very interesting things to get it running, and it's a pain. Go, all you have to do is that. So 1 line of code, and that gives you profiling on your application. So we'll quickly run it. Let's see. Hopefully I killed, yeah, okay. I did not kill this one. Okay, so we still have this same server running. This command says use the profiling tool, hit that, and give me a CPU profile. So that takes 30 seconds of CPU profile. We can try and generate some CPU usage by just refreshing the page for a bit. Yeah, so this collects 30 seconds of CPU from your server. What is the CPU doing in that 30 seconds? So you can enable this without any overhead on your application, going, things are a little weird now, I would like to see why. Get a 30-second CPU profile and then analyze that offline. So that is pretty useful. This says it recorded for 30 seconds, with a total of 30 millisecond CPU time. So all of that refreshing was only 30 millisecond CPU time. We can ask, let me see, sorry, if I can. No, that's cursor size. Buffer size. Font? Font. That is maybe slightly too big. Anyway, so it says 20 milliseconds of our time went to this function. So here, there isn't really anything very interesting happening because we're not doing a lot of work, we're just serving files. We can, however, I think, do that, and we get a call graph. So we know what function called which function for how long and what they called. So we know that 20 milliseconds went to actually reading the files that create file. Yeah, syscall. Which is going down. So actually doing the operating system call. Okay, so let's kill this server and see if we can have a slightly more interesting example. So here we have a web server with 2 endpoints, one still serving files from / one called do. Do just writes hello to the output after doing some math. So that's essentially a for loop running 2 billion times, I think. Yeah. So just doing some CPU work, doing some fake CPU work. So we can run that. And we can, again, profile it. Okay, now I have to go. Do is already open. So you can refresh network tab on the outside. That took 1.7 seconds to loop 2 billion times. That's good. But we might not want to loop 2 billion times. Okay, so there is a way to set the duration of the profile you want to take. I forgot what the flag was. Another part of the standard Go library is a package called flag. that parses command line flags, and it has a built-in -- help. So that's typically what a lot of the tools use. Okay, so now we can ask top. What was the top functions? We could see 6 seconds, which is 99% of the work we did was in the function called do math, which sounds about right. Looking at this call graph, it's a lot simpler. But we have this function that we're calling and eventually ending up in Go math, which took 6 seconds to run. So these are obviously really simple applications. I actually wanted to generate really complicated ones. They do get a little involved. Obviously, if you're doing like 100 separate things, calling 1,000 functions, then this sort of branches out in a very nice tree. But it's a way to really see what's happening now in your application. So I think there's also debug pprof. Yeah, so we can look at the heap. So this is every Go routine currently running on that server and what function it's busy calling. Sorry, zooming in a little for you. Yeah. So a lot of times when your server is sitting somewhere in the cloud, you just have a URL to it. It's very hard to know what's going on. You don't have a debugger saying, quickly stop here, or tell me what's going on. You just don't have that. So this is one nice way of knowing what is actually currently running. Why is it doing what it's doing? And yeah, there are a lot of other things, but I'm running out of time. Okay, so one thing where the profiler kind of fails is when nothing is actually being done. So things are taking time. We still have a similar do function. Instead of actually doing CPU work, we're just sleeping. So things are still taking a second to run. We just don't know why. Did I not start this thing up right? I don't actually have profiling on that. Oops. Oh, and I can't edit it. Okay, so since I anyway don't have time, the profiler will give us a very similar profile to this one, where it was just a bunch of HTTP net calls being done, and we don't really know why it's taking time. Because it's not taking time because of CPU work, it's just doing nothing for a second. And doing nothing seems like an easy way to fix, like, oh, I'm just going to remove the sleep. But sometimes that is me waiting for a thread to do work. And I have to wait for the work to actually be done, but it's still waiting. So it's not me doing CPU work that is actually taking time. And it might be reading from disk. It does take time, but it's something that you have to wait for. And the profiler sort of doesn't pick that up as CPU time, because it's really not. So there is this other tool called trace. And here I have a function. I'm randomly doing either nothing for 100 milliseconds, or I am looping for, I think, 30 milliseconds roughly. There is this tool called trace that I will just show off, because I hope, because I can't remember what the command was. Yeah. So it tells you all the threads that was actually running, so not Go routines, but actual threads that was busy and active. And you can, not that way. You can zoom in on a particular time period and see what function was being run at a particular time. You can also select time periods and see the list of functions that was called. Yeah, and so if you can see where my cursor is, we have this thing called timer proc, which is why it is waiting at that particular point. So it is waiting this 100 milliseconds up to this point, and then doing another do work. So we're still trying to do that work, which is either sleeping or doing work. And at this particular time, it just slept, called timer proc again. So you can look at your application in this way, in like time steps. What was every single thread doing? What function was being executed for how long? Why was it waiting? I mean, here are the timers explicitly saying what start time during your trace. So traces are rather large, even for relatively small traces. So that's why you just dump them to file. It's not so much an online thing, although I did encounter one where you can once again just register an endpoint saying, I want to capture a trace of what's going on now. Yeah, so that was me rushing through tooling. Thank you. And I think I actually finished on time.
I think so.
Cool.
Does anyone have any questions?
Yeah. No?
If not, I'm going to ask a question.
Yeah.
So why should I move my Node.js server to Go?
She knows the right questions to ask to get me talking. So Node is slow. Don't let anybody tell you any different. It is faster than Python, which says absolutely nothing. Python is very, very, very slow. It is pretty much the slowest language you can work in. People use Python for reasons that are not speed. So saying it beats Python really isn't saying anything.
But what about CUDA?
So use Python to set, okay, so she comes from a machine learning background. So you might have encountered something called TensorFlow or, was it Theano? And, Scala? But that's a language. I'm talking about libraries for Python. So those are machine learning libraries that use your GPU to do some really nice work. And a lot of them use Python. But all the Python does is in Python you say, I want this thing to happen, this thing to happen, this thing to happen. Now build me the compute graph. So what it does, it takes all those instructions, put them in C, compiles them to C, and runs the C application. And that's where Python gets its speed, by the way, is it does everything in C. So if you're using a library called NumPy, that is C, that's not Python. To give you an idea of the speed difference between Python and Go, I wrote a neural network for an assignment. It ran for 10 minutes, I think. It's a rather expensive piece of work that had to be done. There were people that wrote the exact same thing in Python and took over 6 hours. So when I say Python is inefficient, I really mean Python is inefficient. So if anybody tells you it's faster than Python, yeah, it's faster than my granny. It really doesn't say much, right? So Node is great because it does event-driven processing. It was pretty much one of the first to really do that in a major way. Everything was event-driven. Your networking was event-driven, your I/O is event-driven, all of that. So that thing where I said on one thread you can do multiple things. So I say, I'm going to wait for some network input and then process it. So I wait for the event. And while I'm waiting, the CPU isn't doing anything. So it's free to do other events. So if you have 1 million network sockets doing nothing, you're really sitting there idle, just waiting for something to do something. And that's really efficient. Go has a very similar mechanic. Okay, in Node, you do that using callbacks. So when there is a message for me on this network, execute this function. Then I want to write something back. When I'm done writing, call this function. So you get this nice nested function stack. Slightly older Node. Newer Node, you get lambdas, but there's still a lot of work for you to do in that. Go does that with Go routines by default. So you write synchronous code, one function after another. So if I were to write, I'm just going to assume I'm in a function. So if I go os.open my file, .txt, and this gives you a file and an error back. And if you go file.read and you pass it some bytes or whatever to read into, this, although you write synchronously, is actually entirely asynchronous. So this Go routine goes to sleep until that file handle is open. So the CPU, the thread it's running on, is free to do other things, similar to Node, except no callbacks. Once again, with the read, when actually reading my bytes that I want, that is essentially putting the Go routine asleep, saying, we'll continue with this code once the file is actually ready to be read, and we'll continue with something else at the same time. So that is a similar way in Go, how you get how you can run like 1 million Go routines at the same time without having 1 million threads running at the same time. Because this is compiled, it is a lot faster than Node.js. It also runs on multiple cores, which Node.js doesn't do by default. You can do some interesting things surrounding that, but work you have to do versus no work you have to do. Writing synchronous code, in my opinion, is a lot more understandable. I want to open the file. I want to read from the file. I want to do next thing, next thing, next thing, next thing. Having to think about when this event finishes, I'm going to have to call this function, and I have to remember to pass context, and I have to... why think about that? That is not... You don't need that to get where you're going. You don't need to do all of that to get done what you need to get done. So write code to get done what you need to get done, and have the compiler worry about when to do the event-driven things and when to swap out your code for some other code, etc. Yeah, so that makes programming in it a lot easier, and I think most of you that have coded in Node would have found it easy. Compile time typing is another thing that's nice. So Node.js, you can write a function with types or referencing variables that don't exist of types that are entirely incompatible. And you won't know that until you hit that particular point in the code, where Go would actually tell you from the start. So in the playground, if we try to output, this is bit shifting 2 by 32. This actually gives compile time error, saying that you can't bit shift 2 by 32 because it overflows your variable at compile time. If this was Node, I would have to run it to that point where I'm trying to bit shift, and then I probably still wouldn't have gotten an error, because it just would have continued and broken and done something weird, like turn into a string, because Node does that. Don't laugh, it's true. It's a pain. Suppose you're writing a big application for a client, and you're asking questions, and by the 10th question, you're calling a function you haven't called in the first 9, and then it suddenly breaks. So you've written code, you've spent 10 minutes getting through that part of your application flow, and then only do you get a type error. And then you have to figure out why, what type was wrong. And you don't have any of that information, where really compile time, it would have been nice to know, hey, the thing I just wrote wouldn't have worked. Okay, you can say, yeah, but I'll write tests for it. Well, A, you're not gonna. Even if you do, you can pass something in the test that you are not going to pass it in real life. So in the test, you can pass it in int, but the type you're actually passing it in production is a string, and now your behavior is different. And you won't know until you actually run that thing in production. So, and if you have to spend 10 minutes to get to a point where you know if your problem is solved or not, and it's not solved, that is frustrating. I've been there the past week. Not fun. Yeah.
Do we have another question now that I've asked you mine? Yes. Okay. Hold on. You have to wait for the mic, otherwise we can't hear you.
They're recording things, I think. It
Yeah,
makes me very nervous, but that means they want to hear what you're saying.
All right, I suppose I could just Google this in 10 minutes. But let's say I want to actually set up the environment on my local machine. What do I need to get?
Okay, cool. That is a very good question. You can download the compiler, so you can go golang download. And that will bring you to the downloads page, which will give you a list of versions, and you can just click on the Windows one. I haven't done this in a while. Yeah. And then download it. You should be able to just click next, 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 and have it work. It's relatively simple. So the other thing about Go that I forgot to talk about, that is a really big thing for a lot of people, but I've gotten so used to it, I forget about it regularly, is you can cross-compile. So from my Windows machine, I can tell it, I want a Linux executable for 32-bit. It will give me an executable I can copy over to a different machine I can run. I can tell it I want it for ARM. So your Raspberry Pi, you can compile that on your laptop, get an executable, put that on your Raspberry Pi, and just run it. Same code, no changes. So I've done this week, where I've written a HTTP proxy, essentially, doing some interesting things. Done it on my local machine, made a Linux build, copied that to a box in America, and just run it on a Linux machine. Yeah, and it's, if you want to see how to do that, you go set go OS equals Linux, go build, and then build whatever. It's going to fail because it doesn't know which one of the very many main functions I want to execute have as an executable. I should be able to go to my Go code. So, okay, this might make more sense for people that are visual. If I do this, this is typically the folder structure that you get. Bin package source. Once you do Go, you asked about environment. You put your code under source, and this is also where you get all your packages. So, yeah. So this particular thing just in a loop spawns a bunch of Go routines and hits a HTTP endpoint downloading a file. So this is just to test bandwidth to see how much bandwidth I can use on a network. So I can go to that and just make sure I'm still building Linux executables. Yeah, go Oasis Linux, and I can go build. And this should then give me an executable called ES that I can just copy to a Linux box and run there. Yeah, not going to demo that now, but yeah, you can also do this apparently to Macs. I don't have a Mac, so I haven't tested that, but you can just say you want to run in that architecture and that operating system. Okay, if you're taking the train, then you need to get your lift.
So, if you have any more questions for Hein, I think you can come chat to him afterwards. Because right now, I need to, unfortunately, those of you who are taking the train, your lifts are about to leave. If you don't want to miss the train, you should probably grab a lift. I'd say meet just outside here. I just want to thank Hein for his awesome presentation. So good job. Round of applause for him.
No way.
We have a gift. Thank you. I had to tell him earlier that I was trying to find I needed to buy some whiskey for a friend. So he told me what he liked. Great.
This is really good whiskey.
Yay! Just so you know, if you're taking the train, Harman at the back there is gonna take you. So everybody run to him and go with him. Otherwise, you're welcome to stick around, ask Hein some more questions, have something to drink, have something to eat if there's anything left, and generally hang out. So yes, thank you very much for joining us for the Rabbiteer, and have an awesome evening.